She would never take a bath. We would ask her, she just laughed because her mama was an opium smoker. She made it with this gentleman Lincoln. They met on a boat, it was sinking. When she should've gone overboard, Mama said no way on my load, only of opium smoke. Am I thinking? Oh, help us, Lord. We can't afford destructive ways. You wanna hear what she says? She would just sit on her fat ass, yell at us, fill up my wine glass. She would tell us how sad you won't never know your dad. Oh yeah, my mama was an opium smoker. Go, mommy, go. I wonder how long she been at this. And I said, Mom, baby, come, can't you see it's got all wrong? My mama was an opium smoker.
You will not be able to stay home, brother. You will not be able to plug in, turn on, and cop out. You will not be able to lose yourself on Skag and skip out for beer during commercials because the revolution will not be televised. The revolution will not be televised. The revolution will not be brought to you by Xerox in 4 parts without commercial interruptions. The revolution will not show you pictures of Nixon blowing a bugle and leading a charge by John Mitchell, General Abrams, and Spyro Agnew to eat hog maws confiscated from a Harlem sanctuary. The revolution will not be televised. The revolution will not be brought to you by the Schaefer Award Theater and will not star Natalie Woods and Steve McQueen or Bullwinkle and Julia. The revolution will not give your mouth sex appeal. The revolution will not get rid of the nubs. The revolution will not make you look 5 pounds thinner because the revolution will not be televised, brother. There will be no pictures of you and Willie Mae pushing that shopping cart down the block on the dead run or trying to slide that color TV into a stolen ambulance. NBC will not be able to predict the winner at 8:32 on report from 29 districts. The revolution will not be televised. There will be no pictures of pigs shooting down brothers on the instant replay. There will be no pictures of pigs shooting down brothers on the instant replay. There will be no pictures of Whitney Young being run out of Harlem on a rail with a brand new process. There will be no slow motion or still lights of Roy Wilkins strolling through Watts in a red, black, and green liberation jumpsuit that he has been saving for just the proper occasion. Green Acres, Beverly Hillbillies, and Hooterville Junction will no longer be so damn relevant, and women will not care if Dick finally got down with Jane on Search for Tomorrow because black people will be in the street looking for a brighter day. The revolution will not be televised. There will be no highlights on the 11 o'clock news and no pictures of Harry armed women liberationists and Jackie Onassis blowing her nose. The theme song will not be written by Jim Webb or Francis Scott Keys, nor sung by Glenn Campbell, Tom Jones, Johnny Cash, Engelbert Humperdinck, or The Rare Earth. The revolution will not be televised. The revolution will not be right back after a message about a white tornado, white lightning, or white people. You will not have to worry about a dove in your bedroom, the tiger in your tank, or the giant in your toilet bowl. The revolution will not go better with coke. The revolution will not fight germs that may cause bad breath. The revolution will put you in the driver's seat. The revolution will not be televised, will not be televised, will not be televised, will not be televised. The revolution will be no rerun, brothers. The revolution will be live.
All right, how about a little quick trivia for Bitcoins? In the movie Sneakers, what is the name of the character that Dan Aykroyd plays? Nope. Who said it? All right. Bitcoins. Blink. Let's see. Let me find another one. Okay. All right. In the movie Back to the Future, what was the name of the school principal who was played during both Marty and his parents' school days? Anyone? The principal's name. Back to the Future. Come on. Oh, this was a... Okay, who said Strickland first? Somebody. You... Oh, you guys don't count. You guys... I'm just kidding. All right, well, you're going to have to come find John for a Bitcoin then.
I know John. That's my guy.
Let me try. All right, I'm going to introduce our next speakers. Our next talk is called Movement After Initial Compromise. We have two speakers. Matt is a red team security engineer conducting red team operations and penetration tests for 6th Gen. He has 7 years of experience in the information security field and operated on an NSA certified DoD red team. He's also a U.S. Marine Corps veteran that specialized in signal intelligence. Thanks to our veterans. And also Colin Hartley. Colin is a persistent cyber operator for NSA certified DoD red team. Enough said. Thanks, guys.
All right. Like you said, our talk's on movement after initial compromise. Harley and I met. He was he's still active duty. He can't say where he's currently working right now. But I was a contractor there, and we hit it off, and I learned a lot from him. I hope he's learned some from me, and we've worked together for a while now. I left him to work at 6th Gen, but I'm saying that's us because we're both newbies and we're babies. It's our first time presenting. And we've gone to a few conferences, and a lot of people spoke about a lot of things we're talking about, and then they didn't have video examples, and they didn't go into some of the detail that I wanted. So we only have 45 minutes. We can't deep dive super deep into all of them, but I hope that people learn a lot and take a lot from the information. All right. So my name is Matt Batten. I go by Sleep Zero, which there's two meanings. So in Cobalt Strike, that means interactive mode. If anybody uses Cobalt Strike, which is a C2, right? Command control. And it also means I don't sleep a lot. And then I have a GitHub. I've created some Python scripts for logging of Cobalt Strike as well. It'll take it all and then output it to CSV. And you can import it into whatever you want. And it's super useful. You can edit it to do whatever you want, utilize it however you want. So I currently work at 6th Gen. It's the best company and job I've ever had. My team's amazing, all brilliant minds, and they really look out for me, and I'm just super happy. I get to work from home too, which is really nice. It's a big plus. So my husband, I was recently married in May, and red teamer, pen tester, developed, and like you said, Marine Corps vet, and also cat dad. And so there's my wife hugging R2D2. Thought it was funny. Us married. I don't know if she knew I was putting this picture in there, but it made me really happy. And pissed her off. She's up there, so it's funny. And then there's my cat. Always looks pissed off when I drink coffee. I love dogs too, but yeah, it's true. It's probably get to work. All right.
My name is Colin Hartley. As you can tell by the spelling of Colin, I normally just go by Hartley because of the military and because it's hard to understand. I'm an NSA certified red teamer and active duty military. I promise I'm not spying on you or in your computers. I promise that. I'm not married, but I'm older brother. I take pride in my little sisters. Red teamer and penetration tester. He's the cat man. I'm the dog man. And moving forward.
All right, so what we're going to cover is initial recon once on a compromised system. So once you get that initial callback, what you're going to do immediately after, we're going to talk about lateral movement, so how to move to other systems once you're on that network. Port forwarding, so how to send data through a system that you've already compromised to make it look like it comes from the compromised system to the target, so they don't see your attack machine, right, your attack platform. You want to hide yourself. how to utilize tradecraft, not get caught while moving. So a lot of stuff we're showing you. The tradecraft isn't top notch. There's more involved, like utilizing like invoke cradle crafter, like invoke obfuscation to obfuscate your PowerShell one-liner, like stuff like that. Like not just running your UPX against or whatever. But this will give you a good baseline if you're new into getting a red team, or if you're a blue teamer trying to understand what red teamers are doing. I think this will help out a lot. And what tools are being used today? All right. So setting the stage. So we're saying that you already compromised the system. So most likely it was a phishing email or it was physical access, right? Everyone brags and talks about it normally. So they utilize a rubber ducky or a bash bunny. Rubber ducky is seen as a keyboard they plug into the USB that most likely will execute PowerShell one-liner or whatever you set it as, that will call out to your C2, which is a command control that you would then connect to from your attack platform. And then you can say whatever you want through the shell that you now have access to. Example would be, I've heard a lot and I've seen is they speak to a secretary, will say the secretary's name's Bob. Bob, I need access to these servers, you're not on the list. How do I get on the list? Sarah, the IT director, has to put you on the list. What's Sarah's last name? Smith, Sarah Smith. Can I get your business card, Bob? Sure. You take the business card, you step out, you take a picture, send it to an operator in a hotel room. You go back in. By that time, he's already sent an email to her or to him as Sarah, stating that you get access to the servers because he already has a system that he compromised inside and knows their mail server. And it's really easy to send a spoofed email. So then she gives me access and I just plug a bash bunny in every system I see, right? And yeah. So first things first, you're on the system, who am I? I thought it was really deep. It's a really deep question. So who am I on the network? Where am I in this network? How do can I move my current permissions? How do I get system? So like system's gonna be like your highest level permission on the box that you're on, the machine you're on. Obviously you wanna get administrator like domain admin is probably your end goal depending on what you wanna do. And but getting systems, important so you can steal processes on your current machine. Hopefully you have that opportunity. An example that I like to say is utilizing these commands is really important because what if the target machine you're on is not within the scope of the network you're attacking? What if, like when I was taking OSCP, a lot of times I actually exploited my own box. And I just got excited, I got a shell, and I would just start running commands. And then 20 minutes later, I realized that I was running all those tools and attacks on my own Kali VM. And a lot of people aren't honest about that, and I'm very truthful about when I mess up. So that happened quite a lot, and I learned a lot from it though, and that's why these commands are important. All right.
So kind of going into what Matt just said, we're going to go into some commands that can answer those questions, right? You will see later on in the talk that we do have the outputs, and us actually running these on a target system through our C2. So some commands I like to talk on are net group domain admin / domain. Like he said, system is the highest privilege you can get, but that's on the local system itself. Your end goal is going to be exploiting one of those domain admin systems so you can move to the DC or wherever you want on the network. They have high permissions, and on top of that, it can go pretty much anywhere they want. Another one's going to be like net user / domain, shows you the users on the domain. It's not as important as domain admins, but still they have the ability to move to whatever computer they want to. Next slide. Okay. This is just another list of commands like ipconfig, like in his OCP example, if he would have ran ipconfig within his his box or ifconfig, he would have been able to see the IP address was not his target host. So if he saw that, then he would save the time he ran all those other tools, exploits, and commands. The next one is going to be, who am I? This would have told him right away also who he was on the network, who he was on the target, and when he got the output back, he would have known that he wasn't who he desired. Okay, like I said before, we're going to show you some of the outputs of the commands. Like in the top right, net group domain admin / domain. As you see in our network, we're Batman fans, so our domain admin is going to be Joker for our sandbox environment. Net group domain is going to show you the domains that are on the domain itself. On the left here, we have net start. This is just going to show you the Windows services that are ran on startup that are started. And then net local group / domain is going to show the local groups actually on the domain itself. Top left, this is actually one of my favorite recon commands, netstack tac ANO. A is for TCP and UDP. It's going to show both protocols. N is going to put them in numerical value by port. And then O is going to show you the PID it's running at. So if you know, like, you've been compromised, you've been caught, and you're trying to get off the system, you can see our connection right there is running under PID 3344, I believe. And we can go in and kill that process so they won't see that we have an active connection to the target host.
Is there? Nothing's plugged in. Oh, my bad. So again, NetSH firewall show config. You can see if something's like operation mode, it's disabled. You can get a lot of more information about your firewall. Your route print, you can see all the pathways, right? You can see your gateway and all that. Task list, it's going to show you all the service information for each process, right? Your process ID and everything. Driver query, that's a really important one. You can actually do a driver query /B, and then it's FO/FO space CSV, and you can carry it out. And you can actually get a whole list of all the drivers for like future post exploitation. You can mess with that data. So ARP TAC A, so address resolution protocol, TAC A is for all. So it's looking at your ARP cache of systems as previously seen. Your set command shows you all your environmental variables. So the reason, like, if I'm on a target, I just run set right away normally instead of doing a system info because I'm lazy. I don't want to wait for all that data. And I just want to see domain controller right away. I'm like, what's the DC? Set, boom, there's a DC. I know that. Schedule tasks, it's going to show you all schedule tasks. The /B is going to, verbose, it's going to show you more information so you actually know what user that schedule task is running under as, which that's important information for future you, right? So disrespect your surroundings. But who am I? So who am I on the network? So I'm K Batman, right? Echo logon server, that's another command I run, usually right off the get-go, but NL test is going to probably work better. So you want to get the DC, but due to configuration changes on the domain controller or just the Active Directory in general can affect that. So you want to do it's a NL test ds get domain name. But if you just do an NL test help, you can actually see that, and that'll give you the DC right away. All right, that's you.
So our first demonstration, we've now at this point in the test, we have pretty much who we are, where we are, what we're operating against. So now, in order to start the lateral movement, we're going to run power split, and a module within that is called power up. This is going to do invoke all checks on a target system, and this will give us the ability to actually see if there's any method, for privilege escalation right off the bat. Okay, so all of our commands are going to be typed into the bottom left corner. Right now, we're doing a PowerShell tech import because obviously we want to import our PowerShell script that we're going to end up running against the target machine. PowerSploit is the tool suite. Within there, what do you want to accomplish? Privesc is what we want to accomplish at this point. And then what we want to use to accomplish that, we're going to run powerup.ps1. So now that that's uploaded to Cobalt Strike, we're then going to do PowerShell invoke tac all checks. And what this is going to run, you're going to see it blow by pretty quick. It's going to go through a list of set checks that it will look for misconfigurations on the network that it can take advantage of to cause that privilege escalation. What you're going to see blow by here in a second, we do scroll back up to it. It's a ability to do a DL hijacking attack. It's a very common attack used for privilege escalation. What I like about PowerUp is it gives you the abuse function. So you have your right tac hijack DLL commandlet and the DLL path that you're going to want to take over in order to complete your attack. It gives you it right on the screen. So all you have to do is copy and paste. When you're talking about PowerUp, you have to have Goku because that's 13 episodes deep of him trying to go Saiyan. But PowerUp has a built-in module for DLL hijacking. You saw us use the right tac hijack DLL. What that does is it creates a self-deleting batch file on the target with the command you want to run for privilege escalation. You can alter it and change it. And then it creates, using C++, DLL and replaces the hijackable DLL and then runs it. And once that runs, it calls your batch file that you have, and after it runs, you get your privilege escalated beacon back. It will self-delete, so there won't be trace of it unless they're doing active logging of like their DLL edits and batch files in the system.
So going to Wimic, so there's a bunch of ways to do remote code execution. There's great examples online as well, and we're just going to go over a few of them. So that's a Windows Management Instrumentation console. So it's a way of utilizing WMI to get remote code execution of a payload that you already hit on a target for persistence, or possibly you want to move to that target, right? So this is obviously an example for Cobalt Strike. We're going to do some Metasploit examples later on as well in other commands. So there's a turtle.exe that I put in the system32 directory on a target machine, right? So obviously I wouldn't actually name this turtle in a real operation. I would name it something that's already on there, and then I would put 32 at the end of it. I would append 32 or something so it doesn't stand out, and I would time stomp it so they would have the same time as another executable or DL or whatever I put on the target, right? So you see turtle.exe's in there. So currently I'm on the .12, and you can see I'm an administrator. My process is 5796, and I'm going to run a remote dir. So I'm actually dirring it remotely to make sure my executable is there before I just kick off a limit command against the target, because I don't want unnecessary traffic. Even though remotely dirring does add more traffic, obviously, but I don't want to try to call something with Wimic when it's not actually there. So I remotely dir it. I scroll up, I see it's there. Yay. Boom. There's my turtle.exe. I know it's executable, it's payload. And I know when I execute it that I will get a shell from that target machine. What was it? So we always start shell commands because it's through command prompt, right? It's Windows native. You can do PowerShell and other stuff as well, but the node, you classify, or you say your target's IP address. So I'm moving to the .8. So something to think about here is when I do this, it's going to take me a second to realize because I used a SMB link, or I'm linking it with SMB, and the reason I'm utilizing SMB instead of just 443 or 80, right? So 443 is encrypted, yes. 80 is another way to get the callback, but you can use SMB because it goes over wherever. I specified a random high port for this specific one, but SMB is usually over 445, right? Your domain controller speaks over SMB to all the other systems. So because I'm targeting the domain controller to get that callback, you don't want traffic going out 443 or 80 because a good blue team or a good network security team at a company would see that weird traffic. And you'll see a beacon call in a minute, or I should link to it. So it's a binding. It's an SMB bind, so I actually have to link to the target IP. So there's a link. So now it's actually going through my initial beacon to the target, and so that way all the traffic's not 80 or 443 because a lot of times you'll see. A lot of operators, as soon as they get access to a DC or get those credentials, they get excited and they just run 443 or 80 because they just, they'll kick it off and they want that callback. But you need to use SMB, or you can do DNS tunneling as well. It's another way, because 53, right? Because everything speaks over 53 in SMB. All right, sorry.
Going into another type of remote code execution, one thing I want to state is all these types of remote code execution lateral movement are either through stuff that's natively on Windows or within sysinternal suite, which is a Windows side executable. So we're using stuff that's already there on the system machine. We're not just downloading and uploading large amounts of data and payloads to the system itself. So this is going to be a scheduled tasks. As you said, shell we're doing within Cobalt Strike again. So /create, that pretty much explains itself. We're going to be creating a schedule in the target system. Task name is going to be mat.exe. You guys are going to see a lot of mat.exe and a lot of stuff named Matt because he's all about himself. Joke. But the task you want to run, is going to be mat.exe in this case. We're going to run it once. There's many different ones you can decide to do. You can do it on idle, on startup, run it once. You can state a time. And so you can actually use this as a method of persistence if you know that there's not a lot of traffic at a certain time of day. Kill it at the end of their workday, and then when they come back in at 7:30, your task kicks off, you get your callback, and you can kind of blend in with the network to a certain degree. So here's going to be an example of us actually running a sketch task on a target system. Again, we're going to go shell sketch task. We're going to run the command I read to you previously. Create task name. In this case, it won't be Matt. It's going to be turtle. The task run is going to be the turtle.exe we previously utilized in our previous attacks. Since we're going to kick it off ourselves, we're just going to run it once, and we're not going to specify a time. So after we kick it off this one time to start, we're not going to utilize this anymore, just for the sake of example. And we want to run it under system, right? So when we get this callback, since we're going from administrator on this target machine, we're going to run as system, so our beacon should call back as system. Next, we are actually kicking off the scheduled task ourselves. So /run, task name again, turtle. So we know the task is on the compromised system. We're going to the .8 again and specifying the task to run. Okay, success, the scheduled task turtle has successfully been created. You're not going to want to run the command to execute it, obviously, before you get that confirmation message that it's been created. So again, there you go. What I like is it gives you that success back. Success, it's going to attempt to run the scheduled task. Cobalt Strike's very friendly with giving you your syntax errors back pretty quickly and not letting you run faulty commands or commands with wrong syntax against a target system. Okay, and we have a couple of our videos, we're running SMB links still because we're exploiting the domain controller. So a little bit of times we pause and wait to link it. So as you see, we link it. Now we have system on the Joker, the .8, and we're going through our .12. So the DC isn't going to be seeing our Kali attack box on the backside. It'll just be seeing traffic from, a host on our network's communicating to the domain controller via port 445 or the random hive port we specified. The final thing we're going to do, obviously because we don't want it there, we didn't use it for persistence in this case, we're going to delete it. /F is force. Delete is what we want to do. And we're going to delete the task that we created and on the target we created. If you delete the task itself, it's not going to kill your beacon. So you will have opportunities to interact with your beacon as long as you want that day. But the next day, you will have to create a new task or move a payload over. The last form of remote code execution I'm going into right now is a service create, another thing that's used natively on Windows. So the command here with a service create, we're going to obviously want to know our target. Create, here we go with Matt again. And then we have our bin path, stands for binary path, and this is just path to your executable on the target machine. And then for this, once you create the service, we're going to kick it off ourselves, and then make sure we delete it again, for tradecraft, so you're not just leaving started services and leaving scheduled tasks running, because those are easy to query for a blue teamer on the other side. So right now, we're interacting with the .12 again. We're going to be targeting the .8 in this example. Just because it's our domain controller, we want to show that it works from host to domain controller, and the payload will run on different boxes. So right now, we're going to service create. There's our target, the .8 again. That's going to be the domain controller Joker. This time, he named it I Love Baby Turtles. And bin path is going to be obviously the path to the executable we had on the target already. This time, we put the payload in Windows temp. A good thing, what I like about Windows temp is that it's created like on logon, and when the person logs off or system's rebooted, temp will be wiped, so you won't leave your executables on the target for a very long amount of time. It's a kind of way to, even if you do forget to remove it yourself, it will be deleted, so you kind of like CYA a little bit. Okay. This one did take a minute to come back, so should give us the service create, like the success message, just letting us know that it's been created on the target box. I love even when we're in interactive mode, it still takes a long amount of time to call back to our C2. There we go, our create service success. So we know the service is created on that target. And so now we know that we can move forward on our test and we can actually try to kick off the service itself. So there we go, service create. This is us remotely kicking off our service on the .8 again. We want to start it, obviously start, stop. It's pretty self-explanatory. And I Love Baby Turtles, that's the service we created. So if you put spaces in the I Love Baby Turtles or any of your service create, you're going to have to actually wrap that in quotes because it won't read it. We got really impatient here because we didn't wait for the success message. So we just kept trying to link to it. And the fourth time was a charm. It ended up kicking back a system, which is what we wanted to run it under. As you use Joker, there's our process ID. Our callback time, and our SMB link to the DC. What I like about Cobalt Strike is everything's it's very visual, and you get the command line access as well, because the SMB link in the top left, if it breaks or the callback dies while you're on the target, that link in the chain will visually break on your screen. It'll be separated. Also, what I like about the SMB links is the SMB links only call back when you have traffic and input to give the target host. So it's not constantly going to and from. You're not constantly seeing that activity and that traffic. You're just going to see data being given back to you when you're actually running and trying to exploit the target or exfil data. So just because we had a lot of Cobalt Strike to start, we're going to add some interpreter in there for people who are enjoy interpreter or using MSF console. So we're just going to do PS exec. So here we go. We're going to load our actual module itself, Windows SMB PS exec. Obviously, when you're doing interpreter, the nice thing they have is show options, so it tells you what's required. Our port, we're doing SMB, which works with PS exec. So that's already set for us. So all we have to do is set our R host. This is, again, what goes into exploiting our own box. We accidentally set the R host to .12. So if we would have ran this, we would have ran it against yourself. Look kind of goofy. So, make sure we had it right, changed it to the .8. We had credentials at this point. So we set our SMB user and our SMB password. You don't have to, but if you have it, it won't hurt you to use. Run show options again to make sure nothing has been reverted to default and all of your options are set in the exploit itself. And then you can type run or exploit. Either way, it will run for you. As you see at the bottom, obviously you don't want to do port 4444. That's common with interpreter. You're going to want to specify your own port, but for the sake of the demo, we left it by default. You're going to see the interpreter session start up, and then you're going to want to do get UID because you want to see who we are. You want to answer those questions that we asked in the beginning of the talk. A process was created. We go down and run host name because once you're an interpreter, you can go inside a shell. As you see, we're on the Microsoft Corporation All Rights Reserved, so we're within a Windows box. We have our host name Joker, which has been the .8, and now we know where we are and we have our ability to start interacting as a shell or use other interpreter payloads and modules against the target.
Okay. So we have to mention WinRM for lateral movement or moving within a network, right? So it's Windows Remote Management. So it's on port 595, 5986. 5986 is encrypted. A lot of people will argue, and I know that encrypted traffic can be sent over 5985, I'm aware. And it's just another good way to laterally move. And Windows Server 2008, same thing. It's a WRS now. It's just something to be familiar with and know that's already, it's on the Windows targets. And I love that meme because it's true, Windows Server Security, keep out or enter. I'm a sign, not a cop. That's very true. And then, so next one's a remote registry, so registry keys, right? There's just a dude running with a register. So I put a goat.exe on a remote or a target machine on the desktop just so you can see it. Obviously, I wouldn't do that on a real operation again, but it's for pictures and stuff. So, remote registry has to be enabled on the target under your services, right? So if you see that's enabled, then you know you can move as well. So for this one, I use interpreter, and so I already have a shell, and I'm going to add a registry key to a remote machine, and then I'm going to kick it off so that I get a callback from it. And I ended up using the same payload that I originally had this interpreter session on. That's why I'm going to kill my session before the callback. So there it is. I added it. So I'm going after the Batman computer. So that's a .12. So my attack machine is .6. I already have a shell from .10, and I'm going after .12, which is the Batman. So Batman com, that's the registry key location, right? I called it wolf. I'm calling on the goat.exe. And so after it runs, what I'm doing here is I'm shutting down, or I'm restarting the system remotely. So I added that registry key to the .12, and now to get that registry key to kick off, I restart the target machine. So it's a shutdown /m, and then I'm calling on that system through the host name, right? And then TAC-RFT, so time0, do it now, force, right? So I restarted the target box. I killed my session because my payload's about to kick off, and I started my listener. So there's my listener. So my callback's calling to the .6. I'm waiting. I'm then going to show you that the target machine, what the user sees when I execute this, right? It takes me a second because I'm slow in videos apparently. But it's a lot faster when we rehearse, right? But the video is going to come up, the target. So there's my VM, which is the target, go.exe. And then you're going to see me capture, the shell's going to come in. So it's already restarted. I should have pulled it up earlier. and boom, shell .12, right? So now I have access to that system. And that's what a user would see if they were like currently on. They would see the box restart, and then we would just have a shell and be able to do whatever we want. And from that point, establish persistence, hide stuff in there, and laterally move. You don't stay on the box once you initially compromise it. Yep, all right. DCOM, so DCOM's super technical and in-depth. So Matt Nelson's the one who documented it. I just want you guys to be aware that it is a way to do lateral movement. I don't think I'm by far like the expert to speak on DCOM, but it's really important. There's a lot of good resources out there to perform it. All right. Oh, yeah, just you.
So I'm sure everyone here has heard of Mimikatz. It's a thing that's been on AV, been flagged on HBSS and on boxes for a long time now. We're just going to go over a method how we've experienced and we've ran on tests where we don't have to put anything involving Mimikatz on the actual target box. We're just going to use a sysinternal suite, which is Windows Sign, and PS execs in there. We have, in this case, we're going to be using procdump, right? So once we notice that they have sysinternals downloaded on the target host, we're going to use procdump, as you see in the top left-hand screenshot, to target LSAS. LSAS is what Mimikatz targets because that is where the passwords are going to be stored. The SHA-1 hashes, NTLM hashes, passwords are going to be stored since the last reboot of this machine. So what we're going to do is when we have procdump, we're going to leverage it to target lsas.exe, and the give me you see right beside lsas.exe is the name of our mini dump file. This is pretty much going to be the output of the process LSAS, so we can then pull it down to our target Windows attack platform. And when you're doing this, make sure that your Windows attack platform is the same architecture and same year as the target host you're going after. If not, it will not work. So once we have our mini dump in the bottom left-hand corner and Mimikatz, we have also you see on our desktop in the bottom left-hand corner, we're going to run mimikatz.exe, and then you're going to see we're going to take our mini dump file, import it. It's going to say give me.dmp, and then we're going to run sec urlsa log on passwords, and it's just against the give me.dmp, the mini dump file, and then we're going to see the output. There's a very long list of users. So if you kept scrolling down on the screenshot, we had a limited amount of space. You will see clear text passwords. Here you get to see the domain, the username, the NTLM, and SHA-1 hash of the target, of the administrator itself. And this is actually really nice because you're not using Mimikatz maliciously at all on the target system. When me and Matt originally started working together, when I was the experienced one and he was the newbie, this is how he first got domain admin on his first domain controller.
So, I'll say a quick story because it's pretty cool, and I think it teaches people a lot of stuff. So I ended up getting default credentials to RDP to a target, which is like super bad tradecraft if you think about it, but it was the only way I could get on that system at the time. And then I couldn't use WMIC or get remote code execution on any of the targets I wanted. I saw a file server I really wanted. I knew a domain admin had logged into it. So I thought about it, and I didn't think it would work, and it was pretty ghetto. And it's funny though, it was I RDP'd through RDP, and I mapped my share. I moved Windows sysinternal suite to the target, the file server, and then proc dumped the LSAS and created the mini dump file, and then pulled everything back. So everything's Windows signed, so nothing malicious. It doesn't look malicious at all to anyone, because the sysads were using RDP. So unless somebody was on while I was on, then that would have been bad. But I pulled the dump file back, and the reason he said the architecture matters is because it actually took me a few hours, which is embarrassing again. Like I admit, when it takes me a while, it was a x86 target, and I pulled it back at a 64 Kali, and I sat there. I kept running Mimikatz with mini dump, and I realized I had to move to another system or a new attack platform to then get the creds. And then I got domain admin. I'll never forget that. It was the first time. It was really humbling and fun. So, all right. Oh yeah, still me. All right. Responder. You can't talk about lateral movement and moving around a network without responder, right? Super important, super in depth. There's a lot of information. So I love Responder. It's a lot of fun. Any company you ever go to, if you get access to a switch, if you ever walk in there, depending on their port security and everything, they'll never have a lockout when you pull the Ethernet out on the first try. Normally, somebody in here will argue with me after, I'm sure, but most likely network engineers are lazier in that, and they don't want, if something like comes unplugged, not be able to just plug back in and redo everything. So A lot of times when I've done pen tests, I'll go up to a switch, and then we have port security, and I'll just unplug the Ethernet from the switch. I'll plug it in my attack machine, right, my laptop, and I'll do a TCP dump or Wireshark, and I capture their IP address and their MAC. I clone my MAC, I clone my IP address, I then plug into the switch. They're the Ethernet port that I pulled the original one from with my attack machine, because I'm now that machine. And then I would run responder, right? And the reason I'm running responder is to capture hashes that are passed or sent across traffic, right? So LMMNR, it's link local, multicast, name resolution, and NetBIOS name server is what the other one is, which that just, they're pretty much the same thing, just NetBIOS name server runs on IPv4. So here's an example of me capturing a hash from a target user. So what's going to happen here is the target is going to try to access a network resource that isn't actually available. So food, right? I was really hungry, I think, when I was in this video. So I try to go to food, and it doesn't exist. And because it doesn't exist, it means it's not in the DNS, right? It's going to query, it's going to, hey, DNS, is that there? No? And I'm going to be like, yeah, that's me. Send me your hash. And the computer's going to be like, oh, shit. Sorry, language. Oh, yeah, that's me. That's me. And then, dang. And then I get his, so then he'll send me his username and hash, and I can take that hash offline and try to crack it. You can do a lot of things with it. I have an example later. I'm going to utilize multi-relay. My first script I've ever wrote that I was super proud of was automation of ByteBleeder's tool, which was, it was a responder to crack map exec to NTLM relay, and then a PowerShell one-liner, and I just got shells. Horrible tradecraft. It was super cool. So there's a user and the hash, right? That's what everybody wants. You pull that offline, you can crack it, you can pass hash, all this stuff. Runfinger.py, right, Python. The reason for this tool is to see if see what domain and see if SB signing and see the OS version of the target. So when you run that, you're gonna actually see. I'm gonna run against the 3 machines in my lab environment. You're gonna see on .8 SB signing is true, so responder's not gonna work against that. So I'm sure everyone here for their company, they have SB signing on their network, which is a joke because a lot of people have legacy systems and they can't due to Samba and Linux, but so responder will work. So multi-relay, it's an amazing tool for NTLM v2, right? And it'll do HTTP and like nothing like if you have automatic proxy set in your, if you have your proxy set to automatic for your WPAD on your browsers, right, for your images, then you're open to WPAD, which you can actually force WPAD in your responder, which just means that certain resources that they try to access to the internet, when they query it, I would just say, yeah, that's me, same thing, get the hash. So you don't want automatic set in your browsers through your image. You want to go back and set that manually. And here's an example. So this is a .12, again, I know you probably can't see that. So it's a .12, the Batman target, and the user's administrator. And actually, I'm gonna start over. So important, you have to turn off SMB and HTTP in the responder.configuration.file.conf, and that's so that you don't have protocol conflicts, right? So you're gonna turn those 2 off because multi-relay is gonna be utilizing that, right? Not responder, but so you're gonna start responder, or I'm gonna set multi-relay first. So in multi-relay, you can do TAC. You can do the target, so you can specify multiple targets or a range, or you can specify 1. So say you're going after 1 machine, then you can specify user, you can specify all users. So for this example, I'm saying I want this guy, and I'm only going to use this user. Or I'm going to use all users, sorry. This guy, I'm going to use all users. So anybody that passes their hash, any users, I'm just going to relay it to that target to try to get a shell. Which the shell is the end goal here, right? And hold on. So here's me starting responder. I think I'm gonna try to go to a share called hi everyone, which doesn't exist, okay? So it's listening, I know it's listening. I know multi-relay is currently running as well. And then I'm gonna go to hi everyone. I don't know, it's horrible, you can't read that. But. So I try to go to hi everyone, boom, shell. Right, I can dump hashes, I can get over interpreter, or COBOL strike, whatever I want, whatever C2 I want to do. So responder is really useful.
Next, one of the last things we're going to go into is going to be port forwarding. There's many different types of port forwarding. We mostly go into proxy chains port forwarding, SOCKS with COBOL strike, and then Metasploit port forwarding. The good thing about port forwarding is it's it's not like the SMB links we were having earlier. This is using a compromised host to tunnel traffic through. Yes, you're doing that when you push a payload, obviously through SMB link, but this is just for anything you want to run from your Kali box. So in our examples, we're doing scans of a target system from a system within the internal network, so we can see what ports are open on it and anything we can target. So the first video is going to be proxy chains with port forwarding with socks through Cobalt Strike. The file on the right I'm editing is proxychains.conf. As you see in the bottom, there's our attack box IP, port 8000. And then in Cobalt Strike, we're going to do socks and then make sure the port links up. So everything on port 8000 is going to be given through Cobalt Strike. It's going to go through our beacon that we have on the .12. And then for proof of concept, we're running proxy chains Nmap, just an Nmap scan. So we're going to be scanning the I believe we're scanning the .10, the Batman box, or the .10, the Robin box from our .12. So if you're running Packet Capture or Wireshark, you're not going to be seeing that Nmap scan coming from our .6 or Kali box outside your network. You're going to see it internal, if you are in fact running it. So we're looking for ports 22, 445, or 3389. As you see, 445 is open. And 3389 with RDP and 22 SH is closed, which is good for a sysadmin, but Eternal Blue can target SMB 445, so we can leverage that using pushing exploits through our port forwarding to target the end host, so we can move further into the network. Port forwarding through Interpreter. At the top, you're going to see us. Obviously, we have to create our payload. We're using MSF Venom to create our payload in this one. TechP is the payload. We're using reverse TCP. Our host is going to have to match up. Everything in the payload is going to have to match up with everything on our listener. So our Kali box is listening on port 8686. TechF is the format to executable. cat.exe is the executable itself we're creating. And then we're setting up our multi-handler, which is our listener, just to catch that callback once we run it on a remote host. The next slide. This is important because especially if you have insider threat or someone on the internal network, we're using Python, a TechM module, simple HTTP server on port 8080 to host our etc TechF directory. That's where we're holding our cat.exe exploit that we want to put on the host box. So say you have someone insider threat or a cat team or someone that goes out, they can browse to our 192.168.1.6 on 8080 and they can see that executable. Depending on the security settings of the target network, they can download that and execute it and give us our callback back. As you see the GET request on the left-hand side, they are hitting our attack box from the victim. This is just showing you us running our multi-handler. So we're running our listener, and we kicked off cat.exe on the target box. We just did proof of concept within shell to show you our host name is Robin. And then we exited out of the shell and straightened back into our interpreter session, which is where you have to run the port forward add. And as you saw, based on our Nmap scan using SOX proxy earlier, we're targeting the 445 on the .12, so we can then go exploit that because we saw that port 445 was open.
So there's obviously experts on Bloodhound. I'm sure everybody's aware of this and knows what it is, but we can't talk about it without touching it again, right? So Bloodhound utilizes Neo4j, right, which is a graph database management platform. And that's us logging our Neo4j server on the bottom left, server connect, right? And it's a Bloodhound bouncing just ahead. It's cute. Thought it was funny. No one laughs. It's fine. So it's important. So you start your Neo4j server. And the coolest part of this, right? So if you've worked with Bloodhound, you've seen this. So Bloodhound runs, it gathers all the user data, and you get the groups and the users. You know the shortest path to your domain admin or getting to whatever group you want, right? But a lot of people, so it drops the zip. So it actually drops the zip file to the target, and you pull those back, and you upload the CSVs, the Neo4j. You can actually, they actually set it up now where you can do a reverse port forward, and using it's like REST API or like the URI, right? It's like TAC URI. You specify your username and password, or TAC URI. You specify your pass. So HTTP 127.0.0.1, 7474, whatever, 76, something like that. You can actually have all the data go directly in your Neo4j from your target, so you don't have to drop that zip on a target, and that's pretty fun and pretty cool. So you can see your Neo4j just updating. You can do a loop as well, right? Looping is really important because you don't know how much data is going and when the users are active. So that's the zip that I dropped on target because the other way. And there's an example of what it looks like. So this is the shortest path to the high value targets, right? Yellow's the groups, green's the users, and then the red's the box we compromise. And it's super pretty. Those guys are brilliant, obviously. And now we're at the end. So like I have to do references because I don't want to say all this information is mine because it's all out there. And these guys are, again, brilliant. And I love learning from them and just being around them. So all these websites are super useful. And you should visit them all. Spectre Officer, they're awesome. And then people that have influenced us, and they might not even realize it. So I had to put their Twitter handles, or handles, because I follow them super closely. I read all their posts, and they're super inspirational to me. They don't realize it probably, so I'm just watching them from afar. I'm creeping on them, but it's weird. I met a few of these guys. They're awesome. And there's Dwight. I love The Office again. And like that's what I imagine a hacker on a network. It's just like domain admin, network engineer, whatever, like just the same person, just a bunch of different hats. And I thought it was pretty funny. Again, Dwight. But if you enjoyed this talk, like to know more, that's why I do the reference slide. That's why we put the Twitter handles up there. And that's why we're saying message us on Twitter. I love feedback, and I love getting questions and just moving forward with other people and like collaborating. I write in Python. I'm currently working on writing my own implants. And the big thing, so to finish up, something I want to mention is a lot of stuff we talked about is Cobalt Strike and Metasploit, but for those super awesome red teams out there, they're creating their own C2s and their own implants. And that's how they're not, AV is not going to detect that because they're just crawling all those signatures. As soon as Cobalt Strike comes out with a new version, they just, they buy it. Or they'll upgrade their version and then they just crawl it and then they update the signatures and then you're going to get flagged. So it's great that we're utilizing this and it sounds really cool, but creating your own and keeping it in-house is the way to go long-term. That's going to cost a lot of money up front for development for companies, so just so you know. And, do you have anything? That's our talk. We're right at 0. Does anybody have questions, I guess? Sorry. Good. Sorry.
Oh, shit. Questions? We got a couple seconds.
Systems other than Windows and Linux. So you're speaking about systems other than like just basic Windows and Linux systems, right? And how secure are they? So generally if they have an OS, we are Linux and Windows. Oh, sorry. We are Windows and Linux, like that's our niche and that's what we go to when it comes to exploitation. But there's people out there that can exploit anything from like the kernels on like the Windows and Kali boxes, or they can do server-side exploits, or they can do web-based applications. I'm sure if it's connected to any network on the internet, there's someone out there that has an exploit for it or can target it in a way. We just are Kali Windows and Windows Legacy based when it comes to attackers.
Yeah, no problem. Any more? Also, like nothing's really secure depending on like the value. That's like a huge thing. So like if it's super valuable, then yeah, somebody's going after it and you're not secure. And like it's better to look for already being compromised than to just assume that no one will come after you. Right. Yeah. Right. All right. Any more questions? Sorry. No? Cool. Yeah, man. If you follow us on Twitter, no, I'm saying, but we're going to post them. I wish that I already uploaded them all before. I should have uploaded them before this. I believe, are you guys going to post the slide? No?
Yeah.
Okay. So they're going to post slides as well for BSides RDU. And that's why I made these slides so people can use them. That's the thing. Like, we went to a bunch of talks. People spoke about this stuff, responder, pass the hash, all this, port forwarding. Like, port forwarding blew my mind the first time I learned it. Like, I was like, I don't understand. So I'm attacking myself, and then it's hitting things, and it's working. I have a shell that's not me. And so no, these shells will be available. We'll post them on Twitter, or slides. Shells. Talking about hacking all day. All right, cool. Is that it? Sorry. All right, have a good one. Nice meeting all y'all.
So if you guys haven't been here before, this is kind of a tradition at BSides RDU Raleigh over the years that we give out these sneaky books is what they're called for the speakers. So they've got a nice little flask in here with the names engraved. So, just to entice anyone who's thinking of becoming a speaker, submit a talk for next year. You'll get this nice, really cool book. What's that?
Completely,
Better not be. Okay.
completely full.
We can fill it
Full.
up.
Yeah, it's full.
Thanks.
Yeah, dude. Sorry. It's nice meeting you.
Green shirt. All right. John, help me out. Come on, man. I got to read the questions. You give out the coins. I know, right? It's about to be. All right. One more question from War Games. David discovers the password gaining access to the Whopper account. The computer asks David if he would like to play a game. What game does David prefer to play? I heard it first here. I know, it's an easy one. I'll get some more difficult ones. Ready? You all set? Okay, cool. You get him behind you. And the hat, right behind you. What's that? No, it's just a little. All right, so I'm going to introduce our next speaker. This is our last talk before lunch. The speaker's topic is, as you can see, our Docker app got hacked. Now what? Which I don't understand because Docker's super secure. I mean, it's completely secure. Right? Joel has his master's in crypto analysis. He also dabbles in reverse engineering and forensics analysis, malware counter-exploitation, malware obfuscation, evolution, and botnet neutralization. Welcome, Joel.
So as you can see from the slide, this is going to basically be talking about what you do after someone's Docker app has been hacked, because as we all know, they're not always the most secure. They're better than some things, but not always the most. So right off the bat, that is a link to all the slides I'm about to go through. The reason I'm putting it up there first is because there's going to be a lot of terminal session screenshot type things, a lot of text. I've tried to make it as large and legible as possible, but I realize not everyone's necessarily going to be able to see it well. So if you want to even just download it right now on your phone, you can. So I'll leave that up there for a second. While it's up there, I'll give you a little bit of a story as to why I'm giving this talk. Basically, something along the lines of what the title happened. I run a small cybersecurity company that, among other things, does forensics. And one particular day, one of our partners reached out to us and said, hey, we've got someone who was running a bunch of Docker apps on a server and it got compromised. And now they need to know what happened. You know this Docker stuff. Can you guys take care of it? Okay. So one fine summer day, I found myself staring at a host image that had a whole bunch of Docker containers on it. And I had to figure out, well, how am I going to go forensically pull out the information for what went on and figure out, basically what was the story here. And of course, the first thing you do is you sit down and say, okay, before I reinvent a bunch of wheels, let's go see if someone else has made some tools. So you Google it. And Google came back with nothing. By the time I was done, I'd spent a reasonable amount of time in the Docker source code sorting through how all this stuff worked. And when the BSides call for proposals came around, I thought, maybe I can save someone else the trouble of having to do this the hard way like I did. So the goals for this talk basically are going to be, if you find yourself in a position where someone's Docker app got hacked and everyone's looking at you and saying, what happened? How can you go pull out the forensic information necessary to work out an answer to that question? We'll cover what it's like for a live system, which is the easy case. That's one slide. And then we're going to spend a lot of time on what to do when you've basically been handed a cold hard disk. Yeah, there were some Docker apps on this. Tell us what happened. Not quite as simple. Specifically, Docker has a lot of different storage backends, which is how they store the disk state for a container and images and whatnot. We're only going to cover two of them, but they're going to be the two that you're most likely going to run into. The overlay 2 backend, which is the default one that they're pushing everyone towards, and the device mapper backend, which is the one you're going to run into on certain versions of Red Hat Enterprise Linux or CentOS. There are others, but if you wind up in this position, you're probably going to be dealing with one of those two. So, to start off, just to review, what's a Docker app? A Docker app basically, or a running Docker container, is really nothing more than, at least on a Linux system, which is what we'll be looking at, nothing more than an ordinary Linux application that's running, with two caveats. One is there's that nice little box around it, which is basically the Docker daemon using a bunch of Linux kernel primitives to say, okay, we're going to try to make you think you're in your own world. As Dan Walsh famously said, containers don't contain, so that is a little bit leaky, but it's pretty good. And then the second part that makes a Docker container is that this application that's running gets its own dedicated view of what it thinks the file system is. And what's of special interest to us in this case is that the way Docker does that is by kind of stacking layers on top of each other. So instead of just saying, here is a flat directory with your file system, we're just going to like chroot into it and off you go. They maintain things in a bunch of layers, partially so that they can have a base image they can reuse many times, and then all the writes that individual containers do are specific to those containers, and partially due to some of the development-oriented priorities they had when they originally designed stuff. From our perspective, basically for a live system, we're either going to be dealing with, all right, we've got that entire picture, so what can we grab? For a cold system, we're just going to have those little boxes underneath the foo process, which is the different disk layers that make up the foo process's view of a file system. So live capture, how are we going to do that? Well, thankfully, Docker makes this fairly simple. We can actually do live capture almost entirely with just plain Docker commands. It turns out when you run a container, almost all of the relevant metadata for what's there can be dumped out with the Docker inspect command. That's going to include what image, what file system layers that you start with, was the container started on, what did they run, what directories from the host file system or somewhere else did they mount into the container, what kind of privileges did they give it, what were the environment variables, the whole 9 yards. So that's one thing you'll definitely want to grab if you're dealing with a live system that you can control. The other nice thing is that Docker also logs all of the output, standard output and standard error from any container. And if it's got a terminal attached to it, you'll get the input too. So the Docker logs command will give you a nice dump of that. That can be especially useful in situations where someone has compromised a host and then promptly turned around and run more Docker containers of their own, or maybe that's how they got into the host. Oftentimes they'll run a perfectly benign container, like just a base image container, like the Ubuntu one image. But they'll have a terminal attached to it, and then they'll pump in a couple commands saying like, go download Python. Here's this teeny little Python script that's going to basically just set up a port forwarding shell. Off we go. In that case, if you were to go look at what was on disk, you might not find a whole lot, but being able to look at the terminal I/O can be incredibly illuminating. Then in terms of how do we actually get what's on disk for a given container while it's running, this is where the design of Docker and their mindset for making it kind of like a development packaging system more than a secure containing system comes into handy. The way images are built is by running containers that do individual commands, and then each time a container is done, you take that little ephemeral read-write layer and you commit it, and it's just a new layer built into the image. And so when you're done, you've got this image composed of a whole bunch of little layers, each representing the changes from running a specific command. Because that's how images are created, it makes it very easy for us then to capture the disk state of a running container. We just commit it. Now what we'll get is we'll get a new image that is just like the base image that it had, but with one new layer on top, which is exclusively the changes the container made. Then we can use Docker save, and what that's going to give us back will be a tarball of all of those layers. This is especially useful because what you're going to get back is each layer as the differences it had on the one before. So you can look at the top layer you have in that tarball, and it's going to be everything the container changed or added as opposed to what it started running with. This is oftentimes what we're searching for when we're trying to do forensic analysis of a disk drive anyway. In this case, it just got nicely wrapped up in a bow and handed to us. Then finally, if the container is running, the other thing that we can do is we have the opportunity to actually grab process memory. Because a running Docker container is really just an ordinary Linux application, it's just got these constraints by the kernel slapped on it and its own little view of a file system. From the host viewpoint, a process inside the Docker container is also a process on the host. Well, I mean, that's handy for us. As long as you're one of those processes inside the container, you're still constrained by the kernel restrictions that are in place on there. But if you're outside in the host, yeah, if I want to kill a process inside a container and I'm the super user, I can just kill it. It's just another process. Just kill it. So in this case, the docker top command basically just lists off, here are all the processes that are running inside this container. Or put another way, here are all the processes that are running that we've slapped these kernel namespacing and C group constraints on. Once you've got the process IDs and you're running at a host level, you can just say, okay, well, these are processes. Go give me the memory. You can use a tool like gcore or whatever your preference is, and now you have memory images. So if you have a system that's already been compromised, and you suspect you're going to want some forensic artifacts out of it, it's going to be an awful lot easier to go grab them this way than pulling the plug and doing it disk-wise. We're going to go into what to happen when someone's pulled the plug and given you the disk, and sometimes in emergency situations, you don't want to spend the time, just pull the plug. But if you have the luxury of dealing with a system you control that is running with potentially compromised containers running, just grab them this way. So, cold capture. This is the situation where someone has walked up into your office and they've handed you a hard disk and they said, hey, this thing was a host that had a bunch of Docker containers on it and something went wrong. Tell us what happened. At this point, everything on the previous slide is useless. We know that most of the information that we could easily get at with Docker commands is there, but we're going to have to go at it probably the hard way. Depending upon what your tolerance is for potential alterations to an image that you're doing analysis on, you might be able to just load the thing up, stick your own little copy on write layer on it, boot it, run Docker, and grab some of the things that way. In a lot of cases, especially when you have stricter evidence requirements, you probably can't do that. You're going to have to deal with a purely read-only disk and pull out what you can from it. So in that case, if we're staring at a hard drive and we got to pull out information about the containers, where are the goodies at? varlib docker. That is, by default, the directory on any Linux system where Docker is going to store everything that we're interested in. And coincidentally, all of the relative paths that are in this slide from this point out are going to be relative to this location. So the next slide, when it has a path right at the top, that's going to be relative to varlib docker. So, first thing, there's a bunch of metadata we can go grab that's fairly easy to get at. One example is what Docker images were installed on this thing. Well, in varlib docker image, the name of whatever storage background they're using, there is a file called repositories.json. And it basically just lists, here are all the images that were pulled down onto this host. So right off the bat, you can basically presume any container that was running probably used one of these as the base. If it was a compromised host, it might even be interesting to know what images were there, even if none of the containers that were running that you could find when the plug was pulled appeared to be using them. It may have been a very short-lived container someone used to gain lateral movement or some kind of privilege, and looking to see what images are there could be very useful. Another note, for the sake of clarity, you can see there's a bunch of SHA-256 hashes, but I've just truncated them all and made them very short and stuck ellipses after them. I'm going to keep doing that all through the presentation. So you're going to see lots of teeny little, like, 6-character SHA-256 hashes. That's just me truncating them so they fit in the slide, and this is actually readable in the back, hopefully. So there's one place. Another thing, all right, we've looked at all of the images that were pulled down onto this host. What about information for a given image? Well, once again, relative to varlib docker, there's going to be a directory, image, backend. And backend is going to be the name of their storage backend. So in this case, we're going to be looking at overlay 2 or device mapper. So if the Docker daemon that was running on this host used overlay 2, it's going to be image/overlay2/imagedb content SHA-256 and then the image ID. The image ID is just that long SHA-256 hash. In fact, an ID for pretty much anything in Docker is a SHA-256 hash. So that file is a really big JSON file, and it contains pretty much all the pertinent metadata you might be interested in on this image, like, for example, the image's name, the default entry point script. So if you just say docker run image name, what runs? It's going to be the entry point script, the default arguments for it. The build history. This one's interesting. Basically, it's not quite as legible as the original Docker file the image was created with because Docker's renamed a bunch of stuff internally, but you can still see all the basic commands that were run to create this image, when the thing was made, and a lot of other metadata as well. Then what we're really interested in a lot of time is we want to know what containers we're running and what's going on with them. So once again, relative to varlib docker, there's a directory called containers, and it's going to have a whole bunch of child directories in it. Each of those is going to be a SHA-256 hash, which is the container ID. And then inside those directories is going to be a bunch of file, but the one with the really useful information is this config v2 JSON file. That's going to be more or less equivalent to what you would get if you'd run docker inspect while it was running. The other important thing to note is that containers, when Docker runs them, aren't always deleted when they stop. By default, they're left there. So this would be, what you're going to expect to find in that directory will be all the containers someone ran at some point and didn't get rid of, and all the containers that were running at the time when someone pulled the plug on this host. And there's a lot of useful information you'll find there. Obviously things like the name of the container, what was the ID of the image it was based off of, driver, which is what storage backend was used. Especially interesting when you're trying to build a timeline for what happened, the time the container started running and the time it finished running. Path and args, just because an image has a given entry point and arguments for it that run by default does not mean that when you run a container using that image, that's what you have to use. You can specify something different. But if whatever it's going to be is going to be recorded in this container configuration JSON file. Also, all of the environment variables that were passed into this container. Mount points. This can be especially interesting. If you're looking and you're seeing a container that has mounted the root file system, just slash into the container itself, that's highly suspicious. That's probably the kind of thing you're going to find in a container that does something like, dumps the etc password file or adds something to a cron tab or some other way to basically gain persistence on the host. Obviously, there's other things like permissions, settings that could be added that would give them excessive permissions to access the host. There's a flag you can use in Docker run, which of course, now that I need to say it, I immediately forget what it is. Starts with a P, blanking. Anyway, there's a flag you can pass to Docker run that basically says, yeah, all that nice little box we put around your container, throw that out, let this thing pretty much have access to the entire system if it wants it. And at that point, containerization is not really containing anything. It's more being used as a way to just deploy a software package so that it kind of has its own file system and isn't messing with other stuff. That's another thing to be looking for. The other interesting thing, back when we were looking at the live forensic capture, there was that Docker logs command. We know that could be very useful, especially if someone's running what seems like a benign container, but then issuing a bunch of commands to it over a shell session on a TTY is connected with a container. How do you grab that? Well, Docker logs is just pulling that out of whatever log storage system Docker was using. Oftentimes the default for log storage is the JSON backend, which basically just dumps another file in this directory, container ID-json.log, which is going to have all of those logs. If it's something else but still stored as a file, that log path value in the config is going to tell you where you can go find those logs, which once again can be very illuminating. I believe for the JSON backend, you also get timestamps for when individual input and output was done, which also can be very useful if you're trying to build a timeline and someone's done something like run a base Linux container and issued a bunch of commands to try to gain persistence somehow. So that's all fine and good for metadata. But what do we do about disk content? And this is where things get a lot more interesting. So you're staring at that disk someone's handed you in your office, and you want to go find out, okay, well, what did the file systems of these running containers look like? What were the changes that these containers made based off of the base image? So this is another picture taken from Docker's documentation of roughly what a Docker container file system storage is going to look like. Docker basically has all the different layers for an image. Those are read-only. And then on top of that, they stick another layer, which is read-write. And anytime the container wants to write something, it's going to get written into that thin read-write layer. Anytime it reads something, it starts at the top, looks, is that file or block there? Yes? Great, pull it out. If not, keep going down. So you basically have this stack of layers of file system or disk data that where each layer above kind of trumps the layers below, and each layer is basically including changes on the layers below. The trick is, how's all this going to get stored? So to consider that, let's have a small motivating example. Here is a really small, simple Docker container. So the Docker file, which is going to basically create the image of what our container is going to look like, does only a few things. One, it says we're going to base off of the Alpine Linux base image. So we're probably going to go pull that image down from one of their repositories and then start running these commands to build the image for our container. Then, since this example, we're basically simulating a fruit basket, we're going to add a lemons file and a pears file to the fruit directory. Then we're going to add an entry point script to run when this image is actually invoked as a container and say, hey, look, this is the entry point script, go run it. In the entry point, this will run when the container is executed. It's basically going to add apples to the fruit basket. It's going to change our note on lemons. It's going to add a durian to the fruit basket. And then we're going to, for the sake of this example, make sure all of those changes are synchronized to disk, so nothing just stays in memory. Then we're probably going to throw the durian out of the fruit basket because though it looked interesting, we couldn't handle the smell. And because we turned our back and the pears instantly overripened on us, we get rid of those too. So with this motivating example, we'll then look at what are the results we get for overlay 2 storage backends and device mapper backends, and how do we extract them. But before we get to that, what is it we're expecting to find? Well, at minimum, we're going to expect to find these 3 different layers stored somewhere, somehow. At the bottom, we're going to expect that Alpine image, Alpine Linux base image that we're building everything on. Somewhere in the middle of the stack, or at the top of our image, because remember, it's going to make multiple layers trying to build that thing, but when it's done building the image, we are going to expect to find a fruit directory that contains only lemons and pears. Then when we run the container, that thin read-write layer is going to be written down to the disk, and there we're going to expect to find apples and lemons, but no pears. And at least no remaining file for a durian, but maybe if we're lucky, we'll be able to find evidence the durian existed at some point. So this is what we're expecting to find as we go into this. So, first storage backend. Overlay 2. This is the default insofar as Docker can push it. This is what you're going to run into most of the time. In fact, I think right now, for most all Linux distributions, except for some versions of Red Hat Linux and CentOS, this is what will run by default, unless you happen to have a host file system like BTRFS or ZFS, in which case it's going to go use that. It's based off of a Linux kernel module called OverlayFS. The way it works is basically by each layer is stored as a directory. And what that directory contains is just other files and directories that are different from the previous layer. So if you've added a new file, it's going to add a new file to that difference directory. If you change a new file, change an existing file, it's going to add your change version of that file to the difference directory for that layer. If you remove a file or a directory, it's going to find some way to kind of add something, kind of like a tombstone, and they've got different ways of doing that, to show that that particular file or directory has been removed as compared to the previous layer. what the overlayfs kernel module does then is if you give it a bunch of these different difference directories in a mount command, it can basically layer them all together, just like in that picture where at the top, what you've mounted looks like a nice flat file system. And anything you write gets written into the top layer, and only the top layer. But all the reads are going to check each layer from the top down until they find something that matches and then hand it back. So in this particular case, when Docker is using that, that means that all of these overlayfs layers are going to be stored in the host file system. And that's going to wind up being interesting later on. But of course, the first thing we have to do is we have to figure out, well, how are we going to go find these layers? And of course, that's not maybe quite as easy as we'd like, but it's not all that horribly painful. So here's a directory tree. Basically, we start at var-lib docker, and there are two children directories we'll be looking at from there, image and overlay2. Image on the left, overlay2 is on the right. We've already seen other paths that started with image, some kind of backend, and then something else. Well, here the backend's overlay2, so we're looking at image, overlay2, layer DB. That layer DB directory is basically the way Docker tries to keep track of what are all the layers in all of the images and containers I have. For containers, there's a directory called mounts. And what will be inside that will be, once again, a whole bunch of SHA-256 hashes that are the container IDs for the containers that had run at some time. There'll be a bunch of files in there, but the two in particular we're interested in is one called mount ID. That's going to have a SHA-256 hash, and if we go look in that overlay2 directory under the var-lib docker, we'll find a directory with the same directory name is that hash. Then there's going to be, once again, in that layer DB mounts container ID directory, a parent file. That parent file will contain another SHA-256 hash inside of it, and that points to basically the next layer. But since you're running a container, the next layer is going to be an image layer. The image layers aren't in a mounts directory, they're in a SHA-256 directory. Why? I don't know. There would have been no collisions if they were using SHA-256 hashes for all of it, but this is the way they wanted to do it. So similar kind of structure. Instead of a mount ID, you have a cache ID file that points over, okay, this particular overlay2 directory, and then a parent file that will point you on to the next layer. To basically find all the layers in a given container in its image, you just start with the container, look for the parent file, move on down, until you finally hit a directory that doesn't have a parent file, and that one's the bottom. So here, basically, I've kind of cut out the other layers that we're not interested in. We just have the container layer, that image layer, and then probably the Alpine Linux base layer. Over in the overlay2 directory, you'll have all of those SHA-256 directories, and inside of them a directory called diff. And that diff directory is the overlay2, or the overlayfs difference directory. So, given a container that looks like this, we'll make note of the overlay2 storage hash for the container read layer is A23520. If we want to go say, all right, that's fine and dandy, I found all the difference directories, but I want to see what the container was looking at when it was running. We have to mount the thing. So thankfully, that's not too terribly painful. You make a directory you want to mount it in, then you say mount, the type will be overlay, the source is overlay, and then because we don't care about writing, because we're not going to try to modify it, we can just say, for options, it's going to be read-only, and instead of trying to give it a merge directory and an upper directory and all that, say, here's just a whole bunch of lower directories. We're only going to be reading, so all you have to do is just stack these together. We're not going to worry about writes right now. And if we look back one, you'll see, if you look at the three different truncated hashes on the right side, you'll see, here they are again, in that lower dir options section, listed in the same order. The first one's the container read-write layer, and then you go from the image layers from top down, and you mount it. And if we go look inside that mounted directory, lo and behold, there are apples and lemons, which is what we expected when the container's running. Apples are there, pears are missing. So that's nice. We can actually now take a look at what the container itself was looking at before someone pulled the plug. But let's say we want to look at what the container would have had at the moment it was started, the top image layer. Well, that's actually pretty simple. In fact, the next slide is going to be almost exactly the same as this one with about one change in the mount. Here we go. Instead of 3, now there are 2. We just took that, that very top A23520 diff directory that was the container read-write layer and left it off. Now it's just the top image one all the way down. And if we look inside that mounted directory, what do we find? Well, we find lemons and pears, which is good. That's what we should find. That's what the image was set at. So that means we can now mount both the container, what the container viewed, and what the container started with, and we'll look at them side by side. But a lot of times when you're doing that, what you really want to see is, well, what's the difference between these two? In that case, OverlayFS actually made it kind of easy for us. Because all of these diff directories are literally just differences in between layers, we can just go look at the diff without having to mount anything. So here is the diff directory for the fruit subdirectory in the container read-write layer. Apples is there, lemons is there, and pears is a character device with a major and minor number of 0. That's basically the way the kernel OverlayFS module denotes a file has been removed. They just make these 00 character devices. And then for directories, the way they denote they're removed is they'll just stick an extended attribute on them. So all right, we've figured out how to mount the container read-write layer. We figured out how to mount the image layer. We can realize that a lot of times exactly what we want is just by looking at this diff directory without doing anything at all. But what about that durian? Remember, the container entry point script creates a file called durian, and then after its sync changes to disk, promptly turns around and deletes it. Sometimes, especially if you're dealing with a container that was created by a malicious actor, they're probably going to pull some things down the disk, make use of them in memory, and then promptly delete them from disk. We're not going to find that at the lower image layer, and we're not going to find it on the file system for the container layer. Is there some way we can still get at it? Well, if this were a normal host, you could go about using normal forensic tools to try to see, okay, well, the file may have been deleted, but is the inode for it still lying around somewhere? Remember back when we introduced Overlay 2 backend, we noted that since these are just directories of differences, everything's on the host file system. In the event that something like this happens and a container's been compromised, or a host with containers that has been compromised, there's still very good merit in grabbing the entire disk image for the host. Because in this particular case, if you've done that, you can go actually find the durian. In this case, I'm just using two commands from sleuthkit. One where I'm saying, okay, here's my host file system device, devsda1, and here's the full directory to where the fruit directory in the overlay to diff for the container read-write layer is. What was the inode for that? Great, now it gives me the inode. Then I use another command. I say, okay, here's the device, here's this inode, list the files that are in it, and by the way, let me know if there happens to be anything still dangling around that got deleted. And lo and behold, there's the durian still there. So since Overlay 2 operates on a file system level on a file level, in order to grab information like this, we're still going to need a full forensic image of the underlying host disk. Now, the nice thing about all this is a couple of months ago, the Google search for what do you do with Docker storage forensics got slightly more useful. A guy named Romain Gaon over at Google created a nice little Python program that will basically automate mounting Overlay 2 and the older Overlay and AUFS storage backends. It's called Docker Explorer, and you can find it in Google's GitHub repo there. So if you ever find yourself in a position where all you really want to do is just mount the things, this might be an excellent place to start. So this brings us to the second and slightly more interesting backend, which is Device Mapper. This is the one that you're probably not going to run into unless you're handed a host image that was either Red Hat Enterprise Linux or CentOS, up to, I think, like the very most recent version of Red Hat Enterprise Linux. The way this one works is by using the Linux kernel device mapper system and the Linux volume management system, or logical volume management system. Basically what Docker does is it says, okay, we're not going to store things in the host file system. You're going to give me an actual disk for this thing. We're going to entrust that disk or disks to LVM, and I'm going to go make a volume on that disk that is going to be the base device. What they're going to do on that base device is they're going to go set up a file system. In a lot of cases I've seen that file system is XFS. and they're going to leave it completely blank. Then, every time they need to make a new layer, they're going to snapshot that base device. And if they want to make a layer on that layer, they're going to snapshot the first layer to get the second layer and have the new changes there, all the way up till they've built all the layers for an image. When they run a container, they're going to snapshot the top device of the image and get a new device that will be used for storing all the writes from the container. So in this case, instead of dealing with files and directories, we're going to be dealing with block devices. And instead of finding the data in convenient places under varlib Docker, we're going to have to go mess around with device mapper and thin pool snapshots to be able to get our hands on it. But before we can do any of that, we still have the same problem. How do we find the layers? In this case, thankfully, it's more or less exactly the way it worked with overlay.fs. Except we note here, varlib Docker image, instead of saying overlay2, now it says device mapper. But everything under that on the image left side remains the same. It's still the same layer DB directory structure, still the same parent pointers to each layer beneath, still the same mount ID and cache IDs. What's different on the right is instead of having an overlay2 directory and a bunch of diff directories underneath, we have a device mapper directory with a metadata subdirectory and a bunch of files that each contain metadata we're going to need to be able to try to get our hands on the virtual block device for a given layer. Before we get our hands on it, first we're going to have to look at how we go about doing that. So the nomenclature here can be a little bit confusing. DM setup create. It makes you think, okay, well, I'm about to create a new thin pool layer. No, we're creating the device for an existing thin pool volume. DM setup is the command you generally use to interact with the device mapper backend. In this case, we're going to create a new device. Table is the option you hand to basically say, okay, here's the information to go with. And then we're going to have to give it a couple of things. A starting sector off of that base volume, the size in sectors that this virtual snapshot device extends. It's going to be a thin snapshot, so we say thin. Then for thin, we have to give it what's the base pool device we're doing all of this off of, and what's the volume ID. So all of these little layer snapshots are going to have different volume IDs. So how are we going to go about doing this? Well, to access one of these layers, first of all, note the asterisk. You actually have to have the Docker volume LVM mount activated. That's a little outside the scope of this talk, but if you run into that and you have some difficulty, just Google forensics wiki LVM, and there's a very nice explanation on how to do it. What that will get us will be a device called /dev docker thin pool. So that's the base device. That metadata file from the branch on the right we saw slides back, that's a JSON file. It's got a couple of fields in it. The two we're interested in are the device ID and the size, because that gives us the remaining information we need to hand the DM setup. So we'll hand DM setup, create, give it whatever name we want for this new device table. It's always going to start at 0. And then the size is the size from the metadata file divided by 512. And that's because device mapper always uses sectors of 512 bytes. Because Docker is recording the size in bytes and device mapper wants it in sectors, we have to divide by 512. Thin, dev, docker, thin pool. And then the most important part to figure out which layer are we getting is that device ID. Once you've done that, what you'll have is a regular, ordinary Linux block device, just like you would have for a physical hard drive, sitting at dev mapper DK my container. And if you look at it with files, say, hey, look, this is an XFS file system. So at this point, gaining access to the data is fairly mundane. Make a directory to mount it on, mount the device onto the directory you want, with one little caveat. If you try to do this twice at the same time, the second time is probably going to fail, unless you put this no UUID option in. And the reason for that is, remember they had that base device at the bottom, and they put a file system there that's empty. And from that point, they're just snapshotting it. Well, the file system is going to have a UUID built into it. And all the snapshot of file systems are going to have the same UUID built into it. So when you go try to mount the XFS file system, once it's like, great, yeah, this UUID is not in use, we're good. Then you try to mount a different one. It's like, no, you already mounted that. And you have to say, well, actually, we're kind of breaking your expectations for how universal this universally unique identifier is. It's actually different, trust me. Just ignore that, it's okay. So if you leave that off and you run them out the second time to try to get at a different layer and you get this error that makes it sound like it's corrupt, it's probably not, just add that on. All right, so that's how we got at the container read-write layer. Sure enough, we've got apples and lemons. So what can we do from here? Well, what we have at this point are these thin pool devices. We can get one for each layer. The process is exactly the same, whether it's the container read-write layer or one of the image layers. Just go use the layer DB chain, figure out which metadata file it is, pull out the device ID and size, and off you go. But the really cool thing is, this more or less acts like what we have are these little virtual hard disks. So instead of having to monkey around with doing things differently, if you really wanted to, you could just use your imaging tool of choice and just image one of these things and go to town later. The nice thing is that because you have the lower layers, you could say image the container read-write layer and image the image layer directly beneath it. Now you'd have two disk images and you can just compare them and see what the differences are. The other thing, and this one's for those who are reckless or bold of heart, there is a tool called ThinDump. It's not terribly user-friendly. You're going to have to muck around with the kernel to get a metadata snapshot. But what it will do is basically dump all of the metadata that the device mapper kernel module is maintaining for these thin pools. The reason that's useful, or could be useful if you want to go that route, is that if you think back to that, let's see if I can actually find that diagram again real quickly. Here. If you look back at this diagram again, you have a base device and a whole bunch of snapshots on top of it. And we know anytime you have to do a read, it's going to start at the top of one of those little towers and go down until it finds something that matches. Well, all the device mapper is actually doing underneath the hood is it's got that big base device and a volume underneath it in the LVM storage pool. And it's got a whole bunch of blocks there. And so it's like, okay, I'm going to start handing out blocks to people. So for the first base device, it gets a whole bunch of blocks. Then when you do a snapshot, anytime you make a change, it's going to hand out a new block to that snapshot. And so now the data for that snapshot from that change is going to be stored somewhere else in the volume. What Device Mapper is doing inside is it's just basically maintaining a nice little list of, okay, given snapshot, which blocks in the snapshot point to which blocks in the volume. And that's it. That's all it really is. All it does is if a new write's done, it's just going to change that and say, okay, well, you used to point to the block that the layer below was using, but now you're pointing to this new one. So if you're able to, oops, there we go. If you're able to dump out all that metadata with ThinDump, you can basically say, look at, okay, which blocks were pointing to what other blocks at the container read-write layer, and which ones were pointing to what other blocks at the image layer directly beneath it. And now you know exactly which places on disks something changed at. This can be more useful, and depending upon the size of what you're dealing with, more practical than trying to do a block-by-block comparison of both devices all the way to the end. You could be dealing with gigabytes and gigabytes of data and waiting for a while, whereas there might be only like 2 or 3 blocks that changed. This would also potentially be a nice way to find the durian. Remember, we created and deleted it. You could go rip open the file system with XFSDB and hunt down through all the file system metadata and find the directory thing it was in, and like, oh yeah, well that was one of those smaller directories where basically we lost all information once the file was deleted. Great. But the block that was changed on disk is still there. So using ThinDump might be one way for the more bold and comfortable messing around with directly interfacing with device mapper kernel stuff to pull out just the blocks that changed and compare them there. In summary, if you're dealing with a cold disk, you've got a bunch of metadata JSON files that will give you more or less the equivalence of Docker inspect would give you for a container or an image. You have this layer DB directory that basically gives you a chain to start from any given image or container or any given layer and figure out what are the layers beneath all of it. And then depending upon what your backend is, you're either going to have the overlay 2 directory that'll have all of these directories of differences, or a device mapper directory that's going to have all these virtual disk snapshots. So I realized this was kind of lots of texty, terminally technical talk, so I made sure to bake in plenty of time for questions at the end. So we have time for that. And as a bonus, I also put together a cheat sheet for you all. It's just a one-page landscape letter cheat sheet that contains the high points of this that would basically get you access to the device mapper overlay backends and show you the layer DB tree and show you where some of the metadata JSON is. So, questions? Yes?
What initiates, you might have said that, what initiates a new layer? Is it just a reboot of the restart?
What initiates a new layer? Well, you're going to get a new layer in one of two ways. New layers are built when you're creating an image, which is basically a series of Docker commit commands. And actually, that's not really true. New layers are created when you run a container. So you have an image, you hand it to Docker and say, run this thing. A running image is now basically a container. And when a container runs, Docker will take it will create a new empty read-write layer on top of whatever else is there. So you get a new layer when you run a container. The way you build up an image full of layers is that, let's see if I can find that Docker file I showed you. Yeah, the example here. So that Docker file, every line in that file is going to create a new layer in the image. The first line is going to go grab the Alpine Linux image. That's my base set, and it's actually only got one layer to it. Then when I say add elements in pairs, what Docker actually does is basically it does a Docker run on the Alpine image, and it basically copies 2 files in, and then it's done. And now it says Docker commit, which takes the container read-write layer and makes it part of the image I'm building up. And it does that for each step.
So does it ever consolidate the layer?
No. Well, no with a caveat. There's an experimental option you can turn on in Docker called squash, so that when you do a build like this, it will, as the final step, take all those layers, squish them together, and hand you just one. But yeah, generally the way you're going to get layers is, by default, it's going to be 1 layer per line in that Docker file, and then anytime you run the image, that extra container layer is slapped on top. Yes?
Is there a significant performance hit from a multitude of layers?
Yes, there is. Yes, there is. It's not a huge hit, but it's enough that if you read the Docker docs, you're going to find repeated in any of the storage backend stuff basically saying, yeah, and since we're chaining layers and layers and layers and layers and layers, if you need high write performance, maybe you should go use a volume for that. The other interesting thing is which backend you use is going to give you different performance trade-offs. So the device mapper one's kind of nice because you're just using this Linux kernel thing that really does exactly what you want. The downside is that for the thin pool, you have to say how large a thin pool block is. And I think by default, Docker says 1024. Now that block's in sectors of 512 bytes. So basically you're guaranteed if I change 1 byte in a file, at minimum, I've now got half a megabyte of data that just got added to my new layer. And that can add up. Overlay FS, the directory differences one, is a little better in some ways. Also the way the kernel module works, the page cache for the file system is useful. So if you have a whole bunch of containers all with a common layer somewhere in the middle, and they're all trying to read that same file, it actually is that same file. Whereas with device mapper, it's gonna be technically the same file system, but different block devices, so things get confused, and it's not always necessarily gonna benefit from the page cache. So if you 5 containers are reading the same thing, you're gonna actually go to disk 5 times. The reason that Red Hat Linux has had to use device mapper for a while is mostly just because they were doing a lot of really cool stuff with SE Linux to try to contain containers a little better than they currently contain. But it didn't play very well with Overlay FS. And I think they just managed to get that kind of worked out. And the most recent version of Red Hat Enterprise Linux 7 can do Overlay FS now. Other questions? Yes.
And this case has started as a forensic examination you have to do. After you did all this, did you find any proof?
Yes. I was actually able to, I mean, it was kind of anytime you run into a case where you're like, okay, well, before I reinvent the wheel, let's go Google. And Google says, yeah, nope. You know you got a fun problem. So it was a fun one, but I mean, it didn't wind up being an obstacle. The nice thing about things like, well, I mean, any kind of computer system. Yes, yeah. I can't really tell you what it was, because obviously it's one of our clients. Well, I mean, it's, when you're doing incident response for people, they don't like it when you tell the stories. But yeah, the gist of it basically is that it was a host that was compromised. Once they did get in, they actually proceeded to advance their hold on the host by means of running more Docker containers. And so if you kind of play back the talk through your head, you'll hear some points where I'm talking about, yeah, they might do this, or grabbing terminal output might be nice. And it's all from experience. Any other questions? I'm kind of blinded, so is anyone in the back there? Going once? Yes. When the container is removed, maybe. It depends upon what the logging backend is. All right, I have to caveat. I haven't tested this. So if you really want to know, grab me afterwards. We can throw up a VM and we'll find out. But I would presume that for the JSON file it would be, because that container, the containers directory that has that containers, like the config v2 JSON file, that's where the JSON log file usually gets dumped, and that entire directory is gone. But the JSON log output's not the only Docker logging output. They've got like half a dozen or more. Like one of them, for example, is journal-d, which is just going to write it straight to the system journal. Obviously, Docker doesn't really have control to be removing things from that, and if they did, I think people would probably get very, very angry with them. Other ones are routing straight off to things like FluentD or I think Graylog. So for a lot of the logging backends, actually, even after the container's removed, the logging data is probably still there somewhere. It just depends upon which backend that they use as to where you're going to find it. Unblind myself so I can, yes, way, way, way in the back. Was that a question? No. Just someone stretching.
All right, I got a question.
Yes.
So you mentioned earlier how the cold analysis is much more difficult than the hot analysis, but my first reaction when I discovered I've been hacked is get it off the network.
Right.
How do you reconcile with shut it down with what we need to figure out what happened?
That's going to come down to your own judgment and your own policies. The question was basically, you have a trade-off between the easiness of grabbing data if the system's still live versus if something's just got infected or hacked on mine, or I've got to pull the plug right away. What's the trade-off? Like, how do you decide what to do? And my answer is basically, it's going to depend upon your own judgment and the circumstances. So in a lot of cases, probably, yeah, pull the plug. It's going to be harder, but I made you a cheat sheet. The one case I would think of where it might be worth considering not pulling the plug is if you're dealing with a situation where you have a high suspicion that the adversary you're dealing with is going to be clever enough not to write anything to disk. In that case, the only thing you've got is memory. So what you might consider doing, I mean, if you think about, okay, at what point do I realize the system's been compromised? Well, probably a little while after it's already been compromised. So there's already a time window the attacker's been operating in. So the question now is, how much more time am I willing to give them, and is the added risk from giving that time worth the payoff? If, for example, you sat down and you wrote yourself a script that could, in the matter of milliseconds, go enumerate every Docker container on a host, pull down all the memory, write it to disk, make sure that's synced to the file system, and then cut power, all right, if you've got an additional time window of a couple of milliseconds, but what you gain from that is the ability to actually look at what the contents of memory was, maybe that's a worthwhile trade-off. Or maybe if it's in something that's a really, really critical system and you're willing to say, all right, I might not be able to solve the puzzle of what happened here, but at least I didn't give them the extra 100 milliseconds. Just straight pull a plug. Ultimately, it's really going to come down to like your gut, knowing your organization, and knowing what your trade-offs are. But yeah, the memory case is the one case where I would consider possibly giving them that additional couple hundred milliseconds, or maybe even a couple of seconds if it's a slow system worth of time. But that would probably be only if you had a ready-made automated tool to do it and just hit the button and go. Other questions?
Put in any effort into building those tools or building tools that can automatically stitch container and data together?
I have not sat down and done that, mostly because my wife and I just had a delightful little boy who's now 7 months, and it's kept me quite busy. Oh, thank you. But I mean, I will say, I mean, one of the things that my company does offer is tailored software solutions. If you have someone who wants to pay for that done, talk to me afterwards. We might be able to make it happen. Anyone else? All right.